This conference will now be recorded.
Good evening. This is Joe Gallo at NCAN, and I'd like to welcome you to our Wednesday drop-in meeting. And we'll get to that in just a moment, but I'd like to just a couple administrative points if we go along. First, I want to point out, as we normally do, that the information and opinions that are expressed in this presentation are not intended as recommendations by NCAN or its representatives for any medical treatment, product, or course of action. You should always consult your doctor about your own personal condition. I would ask you please to make sure that you stay on mute. And there's somebody I need to mute right away. If you can stay on mute throughout the presentation. And it's recommended, although not required, that you also turn off your webcam throughout the presentation. Questions that you have can be entered at any time. Put them in the chat box. Okay, that's the little bubble at the top of the screen. Put them in the chat box and the moderators will manage them and present them after our presenter has moved on. With that, I will turn it over to Howard.
Yes, good evening and thanks for joining us. I'm Howard Walensky, one of the moderators, and we have a speaker tonight, Dr. Martin Tenniswood. He's the Chief Scientific Officer of MIR, and that's spelled small m, small I, capital R, MIR Scientific, which is developing the Sentinel test to detect low-grade prostate cancer in the urine. It's called a liquid biopsy. And liquid biopsies have long been the holy grail of prostate cancer. Dr. Tenniswood, and he's a PhD, not an MD, and his team at MIR's idea is to replace the unreliable PSA test, get rid of the controversial tissue biopsies, rectal and transperineal, and eliminate the MRIs. It's a tall order. Dr. Tenniswood has been searching for this holy grail for 40 plus years. He's a lot older than he looks, okay? I should point out one of his team members is Dr. Lawrence Klotz, a well-known name in this meeting. Dr. Klotz developed the term active surveillance and the concept of active surveillance about 20 years ago at the University of Toronto. Dr. Tenniswood was born in Uganda but grew up in Canada. He got his doctorate in biochemistry in 1979 at Queen's University in Kingston, Ontario. His research was on the prostates of rats. He followed the research dollars south of the border to the United States, where he continued his study of prostate cancer. He'll speak tonight about his research and how it developed into the Sentinel test at MIR Scientific, as well as the broader idea of liquid biopsies. We're not looking at this as a sales effort, but as an educational effort. So Dr. Tenniswood, the screen is yours.
Well, thank you very much. First of all, I just want to make it abundantly clear that I am a basic scientist. I actually went into Queen's University to do my PhD in 1973, and that was at a time when acid phosphatase was actually used as the screen for prostate cancer, serum acid phosphatase, and it was actually started my career before the PSA era. And I'm hoping to end my career after the PSA era because I'm hoping to replace it with better systems. And this definitely is not about the technology that we have at MIR, although I'm going to describe it to you in some detail because I think it can be very useful for discussions. For example, the one that you had last week as to whether or not Gleason 3+3 is cancer. I vote it is. And you'll see why I say that, I think, as we go through the talk. The other thing is, which I've said already, is I'm not a physician, and I will make some comments about the methodologies that are used for diagnosis. I don't mean these in any way as a criticism of the urologists or the clinicians that are treating people for prostate cancer. I actually look at it myself as being a failure of basic scientists to have provided good technologies and tools necessary for the urologist to identify and to monitor and to treat prostate cancer. So my career started off at the university, at Queen's University, and I've continued it over many years, and it's absolutely true. I did come south of the border. I would say I wasn't chasing so much the dollars. I was chasing a lady who is an American citizen and wanted to move back to the States. So I will fess up to that much anyway. The other thing that I think is important to note is that one of the problems that we are facing as a society working on prostate cancer is the idea that there is one and only one way of looking at the disease. I spent a lot of my time developing new therapeutics for prostate cancer. But one of the things that I was told when I was a young scientist and invited down to the NIH to sit on a committee for an RFA for prostate cancer, Don Coffey, who was one of the legends in the prostate cancer field, said to me, because at the time I was working on the molecular biology of the prostate, trying to figure out how androgen receptor worked and how it made the changes it did in the biology of the cells. And he told me that it doesn't really matter how much I know about the individual molecules that are involved in transcription activation of androgen-dependent genes in the prostate. If it didn't impact patient therapies and treatments and diagnoses, I was actually wasting my time. And it sounded very harsh at the time, but I realized and took it to heart that one of our jobs as basic scientists is to do stuff that makes our research has to make the therapy better. And so that's where I've actually come from over the years. I have meandered all over the map as far as prostate cancer goes and the kinds of work I've done. And I decided I was working on a very large project on vitamin D in the prostate when I was working with the individual, Dr. Wang, Winnie Wang, who was my graduate student at the time. And she was the one that actually, under my supervision, discovered the way that microRNAs influence prostate cell life and cell death, and in particular cell death. So that was where this started. And in the course of her study, she did whole genome analysis of the RNAs, and we focused for a number of reasons on microRNAs. I'll tell you a little bit about those in a few minutes. The reason we looked at micros is because we were working on tissue from core needle biopsies, and core needle biopsies, as you're probably well aware, are fixed with in FFP, forward and fixed paraffin embedded sections. And so when you look at them, you get very, very tiny amounts of material. And the easiest thing we could look at, the most stable nucleic acids we could look at for this were in fact microRNAs. And that's where this all started. So I do want to acknowledge that she's been instrumental with this entire process. She's been essentially the hands in the lab that started this. And she now leads a team of, I think, 15 people working on this whole project. So the very quick outline for the talk. I'm going to talk about the current standard of care for prostate cancer because I think it has relevance to what we're trying to change. If you're going to change something, you really need to understand what you're trying to change. I'm going to talk a little bit about active surveillance, things like the entry and exit criteria that you use for active surveillance. I'm going to talk a bit about liquid biopsies, and I'll talk about the Sentinel PCC4 test, which is the test that we have developed, that Winnie Wang and my other colleagues in the lab have developed, and also how the Sentinel test can be used for active surveillance. So that's the outline. I think I have about 17, 18 slides, and I go through them slowly, but you can keep count if you're getting bored. Um, I've taught for 40 years as well, and I know when students are getting tired because they fall asleep in class or they start Googling things. I can't see you guys, so I can't tell if that's what you're actually doing. But if you actually look at the current standard of care for the diagnosis of prostate cancer, there are some issues, partly because the standard of care really hasn't changed since the 1970s. They have changed aspects of it, but really it's the same thing that we all go through. And usually you go to the annual physical, you get a digital rectal exam, and then you have a measurement of your PSA levels. There's a couple of things that people sometimes don't recognize. DRE fails to detect 80% of prostate cancers. It's not a good test. When you do feel, when a physician feels a growth, then that usually does turn out to be cancer. So it's good in detecting cancers that you can feel. It doesn't work well for the most patients, partly because of the location of where the tumors are formed. They're usually in the peripheral zone of the prostate and are well away from the rectal openings. PSA cutoff, so usually it's used about, you can use from, it used to be 4, then it was moved to 3 to 2.5. Now it's being moved down to 1.5 or up to 10. The problem with PSA is the USPS task force actually came down in 2012 and was very critical of PSA as a diagnostic test. One of the issues with PSA is if you use a cutoff of 3, for example, you actually are missing about 25% of what are referred to as low PSA expressing prostate cancers. And about 10% of these, of the 25%, are actually high risk cancers. And it's because they don't express PSA at high levels. It's one of the things that you need to keep in mind, that not all prostate cancers express PSA at the same level, and PSA as a diagnostic tool is blunted because of that. So if you have a PSA of over 3, though, your normal provider will actually recommend that you go get a core needle biopsy. And that's that's where we sort of come into this whole process. Core needle biopsies come in a number of different, I'd use the term flavors, so it's not appropriate in this case, but really they come in different forms. Basically, I'm showing you a diagram here of this traditional systematic biopsy. And basically it's 12 cores normally. It's sometimes reduced to 6 depending on insurance claims and so on, but really it's a 12-core biopsy. And in fact, the real goal of the biopsy, when it was developed using Donald Gleason's technologies, his classification, was really to diagnose prostate cancer and to diagnose specifically prostatic adenocarcinoma, which is what most prostate cancers are. And it's actually a relatively straightforward process. I know that most of you have had much more experience on the receiving end of the core needle biopsy than I have. But basically, if the pathologist can see a tumor that looks like the core needle, the diagrams that Gleason produced, then you have prostate cancer. There's a problem with this, though, and that is that if you look at the core needle biopsies, they miss an awful lot of tumors. And the reason is very simple, that if you look at the quadrant on the left-hand side of the figure, I would suggest to you that the average tumor, even if quite a large tumor, is smaller than any of the letters in that diagram in the quadrant space. So you've got more empty space than tumor, and so it's not surprising that you miss tumors quite frequently. The average percentage of positive biopsies where you haven't missed a tumor is around 50%. So really, it's a guessing game as to whether or not, if you get a 12-core negative biopsy, but you have an elevated PSA, your physician has a dilemma as to what they're looking at. And you can see this down below, because what's been happened in more recent years is the secondary goal of core needle biopsy is to assess the likelihood that a tumor is advanced or aggressive or clinically insignificant, You can choose whatever adjective you want, either almost interchangeable at this stage, or whether it's an indolent, benign or clinically insignificant tumor. And you can see this, the figure on the right on the left-hand side, the diagram here shows you a core needle biopsy. The region that's circled is in fact probably tumor. And this is what you see when you blow it up, when you look at it under the microscope in large areas. You can actually see evidence of a relatively low-grade tumor. But if you go up here and look up here as well, you'll see a different Gleason score. And the Gleason scoring was actually designed very specifically to look at two regions of the same in the same prostate and in the same needle biopsy, and come to a consensus agreement. And it's key to understand that the Gleason 3+3 is consensus. It means that the two most common pathologies that you see in that are 3 and 3. They can be 4 and 3 or 3 and 4. And you guys know that as well as anybody. But you have to go back and remember that this is a consensus. And as somebody in the discussion ahead of time said, that you can have a 3+3 and right next to it, not sampled by the core needle biopsy, you can have a more aggressive tumor like a 4+3. So the problem with the design of the secondary goal is that it doesn't take into account the fact that there's a very complicated relationship in the tumor and you don't know what you've sampled. And I will point out to you that the other thing they do when they're deciding whether you're a 3+4 or a 4+3, what actually decides that in essence is the length of the tumor in the core. So it really depends on if you've gone through the middle of the tumor, you've got decent lengths to measure. If you've gone down the side of the tumor, you haven't got such good lengths to measure. And it's quite a subjective observation that the pathologist is forced to make, okay? So it's a subjective process because the rules used to determine the risk of progression are not well developed. In other words, what you're really saying is they're not very precise. This is not a problem. This is not a fault of the pathologist or the surgeon. It's really, as I said to you before, it's because the basic scientists have lagged behind and not tried to develop more compelling tools, okay? And so one of the other final takeaway points from this, and this is shown again in with the open circle comment, I tend to put these into black is good and the circles are not so good. Sampling error may not capture the most important regions of the tumor. And I'm sure some of you guys have been facing that as an issue. So what do we do with this? Well, basically what people do as a result of that biopsy is they're told to do one of three things. And I want to start off by pointing out to you the context of what the difference between active surveillance is and watchful waiting, because the difference is quite profound, and it depends on your age, general health conditions, and otherwise. Watchful waiting is what active surveillance was originally called, and it was Laurie Klotz that spent many months, many years, in fact, fighting to change the name to active surveillance. Okay, watchful waiting is an approach to a medical problem, and it's not just in prostate. An approach to a medical problem in which time is allowed to pass before any intervention is actually used. And basically what this does is relies on an individual to say that their symptoms are changing to decide if treatment is needed. And basically the treatment isn't to cure the cancer, it's actually to control the symptoms. It's not designed to cure the cancer. In some cases, individuals have other underlying health issues and they can't tolerate surgery, they can't tolerate radiation. And so basically it's a question of palliating the pain if that's the only real option that's left. It's usually diagnosed, reserved for older men, diagnosed for the first time with advanced cancers in poor general health and who are not strong enough for surgery or chemotherapy. And I would point out to you that one of the problems in the US is that you guys are the exception, in fact, because you've had PSA tests, you've gone through looking for the cancer. You've done the PSA, you've done the DREs. You are in the minority in the North American population. More than 80% of the men of the right age, of the age to get actually screened, are not being screened. They don't enroll for screening. So we're actually not doing a good job even at that level. The difference between watchful waiting and active surveillance is a little bit subtle, but it's critically important. It's what Laurie Klotz developed. He wants to monitor the cancer closely. It usually includes a visit with a PSA blood test every 6 months, a digital rectal exam at least once a year, and biopsies, prostate biopsies and imaging tests, either things like multiparametric MRI or micro ultrasound, are also done every 1 to 3 years. And that is how that's being done now. I've just told you PSA is not an accurate diagnostic. Digital DRE is not an actual good diagnostic, and prostate biopsies are hit and miss because of sampling error. The tools that are being used for surveillance are still not what I think are up to par. Okay, and so what happens is, as some of you were discussing earlier, when your results change, your treating physician will then talk to you about treatment options. So there are two things I would comment to you on this. The first is, if you're on active surveillance, there are two ways you come off of active surveillance. There are two different exit strategies that are used. One of which is to transfer from active surveillance to watchful waiting. A number of you I know have been on active surveillance from 10 or 12 years and probably have an indolent cancer that is stable and won't progress in your lifetime. And at that point, after you've been on for 10 or 12 years and you've had numerous biopsies, it's not unreasonable to think about moving on just to watchful waiting, where you can consider yourself cured. That's a dangerous terminology, obviously, but you can consider yourself stable and you don't need to continue to submit to biopsies. And I'll talk more about that later, because that's what one of the things that the sentinel test does for you. So basically, the other way to come off of active surveillance is you've got clear evidence of progression. And at that point, you need to decide that you have, and again, you can go through and choose your terminology, you have moved on to advanced disease or clinically significant cancer. Clinically significant cancers, I think, need to be treated. And I have opinions about how you go about selecting treatment, which isn't part of this particular conversation. But one of the things my statistical help does, I can't say my statistical help, I work with an incredibly clever statistician who has pointed out to me numerous times that after you have had your first PSA test, regardless of the result, you're actually on one form of active surveillance or another. It's actual watchful waiting or an active surveillance. The only difference that it changes when you're on active surveillance is how frequently you get inspected and detected. That's basically what the difference is. So all of us, after we've had our first PSA, I did my first one at 45 because I was supposed to. I've done others since then, obviously. So I'm on active surveillance. It's just that I have a low PSA right now. So if you look at the way we get onto active surveillance, there's different criteria that are used. First of all, very few urologists will put you onto active surveillance if you have patients who have intermediate or high-risk cancer, Gleason 4+3s, GG3s, a serum PSA of greater than 15 or 3 cores involved. The usual approach for that is immediately to look for definitive therapy, usually prostatectomy or radiation therapy. I would point out that, and I'll talk to you about this in a few minutes, but there are patients now in Toronto under Laurie Klotz who actually have Gleason 4+3s, and they've been on active surveillance, and some of them been on active surveillance for more than 10 years at this stage. So the criteria for exclusion are changing, the entry criteria are changing, and they're actually broken down largely by country and by continent. The restricted enrollment that has been developed at Johns Hopkins over the years by Jeffrey Epstein predominantly says that patients who have a Gleason score 3+3, otherwise known as grade group 1, a clinical stage of T1C, who has a PSA level of less than 10 nanograms per mil, a PSA density less than 0.2, and with less than 2 cores involved and less than 50% of those cores actually involved as well. Those patients are good for active surveillance. That is a very stringent criteria. And the reason that 3+3 is being debated as whether or not that's a cancer is that the vast majority of the patients who are 3+3 have a clinical stage of T1C or less, a serum PSA of less than 10, and a PSA density of less than 0.2. 95% of them are going to die of a disease other than prostate cancer, probably in 10 or 15 or 20 years' time. So that's the reason it's debated. If you so basically, in many ways, it's not a cancer. It clearly is, by the way, from the biology of the disease, but functionally in treatment, it's not. And the question is, how do you advertise this appropriately so that it makes sense to the consumer, which is the patient? Okay, so it makes people more willing to stay on active surveillance. The more inclusive criteria that Sunnybrook uses is anybody with a Gleason score of 3+4 is allowed to is actually recommended to go on to active surveillance if they're in generally good health. If they have a PSA less than 15 nanograms per mil, they don't worry about PSA density and they don't worry about the fixed number of cores. The difference between these two is in fact a very interesting difference in terms of the time course of progression. The patients in Hopkins, the vast majority of them who are going to progress within the first year. And that's usually because the biopsy has missed a tumor that's 4+3 or 4+4. They've missed another portion of the tumor and come up with an artificially low Gleason score. The inclusion criteria, if you look at Sunnybrook and Marsden's the hospital in England that has pioneered a lot of this work. And I should also point out that the Erasmus Institute in Rotterdam has done a tremendous amount of work on this as well. But in fact, if you look at individuals that they use, anybody Gleason 3+4 and so on is allowed in, their failure rate, patients coming off, is about the same as the failure rate for Hopkins. But what happens is after Hopkins' first year, when you're on the restricted enrollment, basically very few people progress after that time. With the Sunnybrook criteria and the Marsden criteria, you do get a small population of patients who progress 5 and 7 years after being on the protocol. And that's probably because there are also 4+3 occult tumors in that individual that weren't discovered on biopsy. So basically, the criteria for coming off of that is, and you say people fail on active surveillance, what you're looking at is patients whose PSA levels increase over time. Anybody that's been in the business for very long knows that our PSA levels continue to increase with age. But if you have a PSA velocity or doubling time that's above the average for the age group, your age group, then you have to look at that as evidence of progression. And again, prostate specific antigen is not a very clear diagnostic tool. So what happens with that, of course, is you go back with a rising PSA, you'll go back and you'll have another biopsy, and the biopsy can miss again, or it can come back and find the same tumor and tell you whether or not the Gleason score, the pathology has changed. But then the majority of them will show that if they haven't changed, the ones that have will be recommended to move off of of active surveillance and onto active treatment. So what are liquid biopsies and why do we want to use them? Well, liquid biopsy is a terminology that's actually been coined, I think, probably in the last 5 or 6 years. And it's any test that detects molecules or cells in bodily fluid is derived from a tumor. In fact, it doesn't actually even have to be from a tumor, but it has to be from a biologically significant or clinically significant syndrome. And you can have liquid biopsies in the blood, the seminal fluid. You can use menstrual fluid. You can use tears, cerebrospinal fluid, saliva, or urine. And I'm going to be concentrating on urine, as you will see in a second. And basically what we're doing is using the fluid as a surrogate for the tumor tissue itself. So one of the reasons we do this is because tumors like glioblastoma multiforme, the brain cancer, you cannot go in and do a biopsy, a core needle biopsy, with any kind of ease. It's a very invasive process. Kidney cancer is actually quite difficult to biopsy. Pancreatic cancer, we can't biopsy effectively. These are all very difficult to biopsy. And by comparison, prostate is relatively easy to biopsy, and it's not as easy, for example, as breast, which is actually a surface biopsy, and it's very easy and has a very high hit rate because you can actually visualize the tumor in the breast very easily. So the idea behind the liquid biopsy is it replaces the biopsy itself, okay? And the thing is that we have to decide what we're going to measure. We can measure, the things we measure are referred to as analytes, and we can measure anything. We can measure molecules. We measure RNA, as I'm going to show you in a few minutes, but DNA and proteins are frequently measured in liquid biopsies. And in fact, PSA is a liquid biopsy. It's looking at the PSA in the serum as a surrogate for the tumor. Okay? So these are very generalized terms, but when you look at them, just about any time we take a body fluid and look at it for something that's come from a tumor, that's a liquid biopsy in one form or another. And we can look at free-floating nucleic acids in circulation. We can look for circulating tumor cells in the circulation, and we can look in exosomes. And I'm going to talk to you about exosomes in a second. But what I want to point out to you, these kinds of liquid biopsies are produced by a large number of different companies. And I think the most prominent one people are hearing about these days is GRAIL, which has a pan-cancer liquid biopsy to identify any cancer that anybody might have from one blood sample. It's actually quite an interesting assay. So far, because it's very difficult to run, it can only diagnose patients with advanced cancers in every single case. There's no case where they actually do a good job of defining early stage disease. And what that actually means is they're identifying patients who should already be on therapy. So they haven't got to where they need to be yet in terms of sensitivities and the ability to look for early stage disease. That's one of the competitors that I have to deal with anytime anybody asks me, because they have a very large presence because of their funding sources. So I'm going to talk to you about what we do. And the Sentinel test is actually a very simple assay. It's conceptually. It's based on the analysis of urinary exosomes, the small nuclear RNAs, small non-coding RNAs. It's a mixture of what are called microRNAs and snow RNAs. I'll talk about their function in the cell in a minute. The point behind this is that this actually only requires a urine sample. It does not require any information from any other system. We don't need to know what the PSA level is. We can do this and want to do it all pre-biopsy so that we actually don't do a biopsy. And what it does is it provides a molecular assessment for the health of the whole prostate. Exosomes are secreted from the prostate, from every cell into the prostate, and they collect in the extracellular fluid, and the extracellular fluid drains into the bladder, into the urine. So what it does is it gives you a look at everything in the prostate. It's not just the tumor, it's the normal prostate as well. It's the stromal cells, it's the epithelial cells, it's everything from the prostate. The basis for this test is that we can in fact identify sequences from the microRNAs and the SNOWs that are expressed at different levels or are vastly different sequences in the tumor, and they're not found at the same levels or at all in the normal cell. So we can identify a signature that is made up of a mixture of these different RNA molecules. And one of the things that's important about exosomes is they're membrane bound. That's critical because this means that they're actually, that membrane, the sphere that's formed, captures all of those molecules that are from the prostate cell. It's actually produced in the prostate, and then the entire exosome is released. It's actually not packaged on release, it's actually packaged before release. So it gives us an idea, a snapshot of what's happening in the cell, okay? Those small spheres are extremely stable, and that's a major advantage for us because it means that we can ship urine samples from one part of the country to the other, and all we need to do is to put it on ice. It can take 2 or 3 days to get from a clinic to the lab, and we have absolutely good RNA as a result of that. We have good RNA as a result of that for another reason, and that is that the molecules that we're looking at, the microRNAs and the CD box small nucleolar RNAs and the Hacker box small nucleolar RNAs are very small nucleic acids. They're very small RNAs, and they are themselves very stable. So what the exosomal RNAs have as a major advantage is that they're extremely stable molecules in an extremely stable environment. And that makes it very simple for us to isolate and extract and analyze. Very quickly, I want to tell you that from other methodologies that you can use in the research lab, we know what these molecules do. At least we know a lot about what the microRNAs do. And they're involved in messenger RNA stability and translation. Messenger RNAs are the nucleic acids that are translated to form proteins. And one of the things that is important in terms of all these terms, or this system, is that it's the proteins that produce the phenotype of the cell. In other words, the protein composition of a cell dictates what it does. And it can be, the protein composition of an indolent tumor is different from the protein composition of an aggressive tumor. And all of these processes, the proteins that are produced and how they're produced and how many of them are produced, is actually regulated by the microRNAs and the SNO RNAs that are in the cell. So these aren't a random assortment of RNAs that we're looking at, which are an assortment of RNAs that have a known or partially known function in the case of the SNOs within the cell. So we can go back and look at the microRNAs and the SNO RNAs and say, yeah, I understand now why that's elevated, because it has this effect on a particular pathway that can influence prostate tumor growth or prostate tumor resistance to chemotherapy, for example. So this is the basis of the test. So I'm not going to spend a lot of time going through the test, but I do want to make the point that when you do a biopsy, you're getting a systematic or MRI-guided biopsy, you actually do a pathological assessment of the tumor, and it depends on the ability to find the tumor. One of the things that's important about this is that biopsy can tell you whether you have a monofocal tumor or a multifocal tumor, okay? And we know that there are different issues with them. Multifocal tumors are more likely to be aggressive than monofocal tumors. And if you look at what we do with the urine, we're collecting all the RNAs that come out of tumor cells and non-tumor cells, and they're all mixed together. And essentially what that does is it eliminates any ability of the urine exosome to tell you whether you have a monofocal tumor or a multifocal tumor, monofocal or multifocal tumor. So the downside of this biopsy system, it mixes everything together, this urine biopsy, it mixes everything together, and you can't always tell what kind, whether it's monofocal or multifocal. That makes a difference, by the way, if you're looking at a therapeutic intervention such as HIFU, high intensity focal ultrasound, which can obliterate one side of the prostate and leave the other side intact. You can use that very, very, very elegantly for monofocal tumors, because you can isolate the tumor, know what side of the prostate it's in, and then irradiate and eliminate the other side of the tumor. If it's multifocal, you can't, because you're just irradiating the whole tumor. and it's essentially the same as a prostatectomy. But we can't use urine exosomes to actually monitor that because we can't tell whether you've got a multifocal tumor or not. You have to have MRI, multiparametric MRI, to identify that if you're going to use that kind of treatment regimen. So I'm not going to, as I said, I'm not going to go through the details of the actual methodology in detail. We actually isolate the RNA from the exosomes, we purify it, and we are actually kind of unique in that we are actually looking at 448 sequences at one time. So it's a very, very detailed look at the environment, the microRNA and the SNO-RNA environment of a particular prostate. This is all done with robotic systems. We actually have run 96 plate samples at a time. It's loaded with this AccuFill system that assists the loading onto these what are called open array plates. The open array plates, they have 48 different quadrants on them, and each quadrant actually is able to interrogate 56 sequences. And so we go through this process and use a QuantStudio. It's a process that's based on reverse transcriptase quantitative PCR. It produces the PCR amplification curves you can see on the right-hand side. The top is actually a microRNA set of profiles from one plate, and the bottom profile is from a plate with SNO-RNAs on it. We actually run eight quadrants for each patient, and by the time we've run it, we actually analyzed 442 sequences in the actual algorithm. The other 6 sequences that are there are controls that we have to do to make sure that the assay has actually referred to as spiking controls. But what we land up with is, for one run, one plate produces about 1.7 million data points. And this actually works out to be somewhere in the region of 71,000 data points for each patient, okay? That's taken off of the machine and it's fed into an algorithm that's been written in R programming that actually analyzes those, and it actually determines the central PCC4 array system, gives you a risk classification. It's a complex process, and I'm not going to go through the actual algorithm, but it's actually fairly straightforward. What we do then, very simply, is extract the RNA, measure the expression of the non-coding RNAs. We perform this reverse transcriptase-based qPCR on a high-throughput instrument, and then what we do is analyze the data, and we classify the patients into risk groups that are completely independent of serum PSA. And this can be done prior to a core needle biopsy. In the current research that we're doing, the patients have agreed to do the core needle biopsy and have the PCC4 analysis done at the same time, so that we can actually compare our performance characteristics to that of the current standard of care. And that's actually what we do now, is we use the statistical approaches to assess the status of prostate health. Okay, so this is a very quick and rather messy way of looking at the sentinel test, but this is actually what we do. The actual algorithm takes a patient with all essentially 442 sequences. It analyzes them in the algorithm, and it divides them up, and it dichotomizes the patients into 2 classes. Patients, in this case, along this vertical line in each of these diagrams is in fact the in the diagram is in fact the what's referred to as the classification boundary. Patients that have one, in the case of the first one at the top, patients who have come across with a score that is onto the left of the classification boundary are predicted not to have prostate cancer. The ones on the left of this, on the right of it rather, are all predicted to have prostate cancer. Prostate cancer in this case, if you think about it, it's anybody who's got Gleason grade 3+3 all the way up to 10+10. It doesn't distinguish at this level between what kind of cancer you've got. But what it does do is separate out all the patients that don't have cancer. And it does this with a specificity and sensitivity that's running in the 90–95% range. So it's extremely accurate. And basically, the guys that come through that then have are known to have prostate cancer, we put them through a second level of the algorithm. And what that does is identifies all the patients with low risk prostate cancer and segregates them. And then you have left over from that are patients that have intermediate and high grade cancer. And the algorithm runs a third level analysis, which actually separates the patients into ones that have intermediate risk cancer and high risk cancer. So that's actually what, in fact, we end up looking at. And basically, the GG1 to low, GG2 to intermediate, and GG3 to 5 to high, there's a rough correlation between those classifications, but it's not terribly accurate because these all contain issues with missed biopsies or missing a particularly aggressive segment of the biopsy. And this is an entirely a molecular-based evidence of the entire prostate. So if you look at the if you look at the test system, you guys have all been diagnosed. You've had a PSA, you've got an initial biopsy, you've got a PSA level. And what you can do instead of this, what we're proposing, the test that we're proposing to put out commercially shortly, actually allows you to do a biopsy. You can ignore the biopsy if your physician will let you, but right now we have to gain their confidence a bit. But basically, if you're on active surveillance, you can join and do this with us anyway. Basically, you provide a urine. That's all you need to do. And we then analyze that urine at time 0. And we will report back to you as to whether or not you have low, intermediate, or high risk disease. It may not agree with the biopsy, but certainly if you have low risk disease, that's the equivalent of GG1, which satisfies Epstein criteria, then you can be on active surveillance. If you have intermediate risk disease, which is GG2, which is the surveillance, the standard that's used in Sunnybrook, then you can actually use you can be on active surveillance. And what we suggest then is every 3 months for the first year, you send us a urine, and literally it can be it's a home delivery kit. You pee in a cup, ship it to us, and we ship the results back to you and your physician. It does require it will require a requisition from the physician, from your treating physician. But basically what we do is this is actually technically multiple cross-sectional analyses, which is following the tumor longitudinally. And so what you do is you take another sample at 3 months, another sample at 6 months, another sample at 9 months, another sample at 12 months. The first year you get surveilled significantly because that's the time at which a lot of the patients who have show evidence of progression based on PSA and the rebiopsy, that's the time frame when they're likely to be progressing. And we can do that, and we can identify those patients simply by showing that they cross a classification boundary, whether it's from low to intermediate or from intermediate to high. And in fact, we have patients that are on low who are actually from Toronto, and they're staying on the study, and they're eventually progressing to where they've gone. We haven't got any that are progressing that far yet, but they're going to stay on probably until they get to having evidence of high-grade disease and need treatment. So this is all numbered up as Ks because my statistician doesn't like to use M because that has other meanings. But basically what we do is we analyze this. If you're low at time 0, low at 3 months, low at 6 months, low at 9 months, essentially by that time we're saying, well, it looks like you have stable disease, okay? And then you would continue to be monitored on active surveillance, but you don't need to be monitored that frequently. And for the next 2 years, you'd be monitored every 6 months. And then after that, rather like PSA works out to be, and you'll end up getting your PSAs land up going out being tested every 1 to 2 and even longer years after that. That's essentially what you would do with the urine. On the other hand, if you go from low to intermediate, then you would in fact be told that you have progressive disease and you should think of moving to definitive treatment. So the idea behind this is that we can identify patients. We actually, every patient on active surveillance is their own control patient. It doesn't matter if you come in with low or intermediate, you're always going to be evaluated based on your central score when you come in, and monitored against that. So this is one of the advantages. It's not a question about whether or not your PSA is changing because of your age. And the variations are much more much broader. This is actually the system that allows you to do this very, very effectively. So I think this is one of the major advantages of this. There is another aspect to this which is a little bit futuristic, but my statistical colleague, Dr. Di Rienzo, actually thinks that after the first year of surveillance, he can actually monitor to see whether there's any evidence that there is a change in progression coming. So right now, the test actually says at the point you cross a classification boundary, it tells you you have crossed a classification boundary. When we've run the algorithm on enough patients, Dr. Di Rienzo thinks he will be able to identify patients who are about to change classification boundary. That study will take 3 or 4 years to complete, but at that point, I think we will have a very advanced study test available for anybody on active surveillance. So this is what the test report actually would look like. You can come in to this assay, into the program with low molecular evidence of low-risk prostate cancer. Your test would be low, low, low. You get a complete report on your status as you go forward, and you can see from that that this is a patient that's not progressing. You can start off as a patient that's not progressing, and after 6 months, you can show evidence of intermediate risk disease. One of the things that we think we have to do before pulling the trigger for moving on to progressive disease, I actually think that we need to do another urine test at the 9-month time point in this case to establish that it's still intermediate, because I'm not sure that you don't get fluctuations in these scores based on other secondary morbidities or perhaps an infection. We don't know that for a fact, so we like to wait. We want to set this up so that the clinical decision is actually made after 2 rounds where the patient has a central test that looks as though there is evidence for progression and 2 consecutive time periods. And that's what I want to talk to you about. I'm happy to take any questions. I will also immediately answer the question, are there other tests that do this? There are 2 other tests that you can look at that will do this. One of them is Exosome DX. And Exosome DX is, again, it's a urine test, and it is based on the exosomes, which is why it's called Exosome DX. But it looks at 3 sequences, and it can tell you whether or not you have high-grade cancer. It doesn't distinguish between low and intermediate grade cancer, so it's very difficult to monitor progression. It will tell you that you have already progressed to clinically significant disease. There's another test called Decipher, and what Decipher does is actually doesn't do it the same way. This is actually a test that uses tumor cells from the biopsy to monitor you from over a period of time, and it looks to see whether a series of 22 genes have altered in the course of between biopsies. And it works well, but it does require material from the biopsy. So it's a secondary, it doesn't get rid of the biopsy, it uses the biopsy tissue. So that's essentially my presentation. I'll take any questions you have, and I confess that I will also say I don't know if I don't.
Good. I'll dive in with a few questions, and then the other moderators can switch it around too. Dr. Tenniswood, thank you for your presentation. You don't have to answer that. But what is the status of this test in terms of the FDA? What kind of cost do you expect?
So
And is it actually on the market?
no, it's not. It's so we let me go through the history of this test. We have got the test. We've presented it to the FDA. They gave us FDA breakthrough status, and we are in the process of filing for the FDA PMA. The test is actually being run now, being set up and approved to run in a CLIA facility in New Jersey. And I was down there yesterday setting up the lab and equipment. The test should be on the market in January, but not with FDA stamp imprimatur yet. So it's available, and it will be on the market in January. I'm hoping not before February, but you know.
And what will the cost be?
So the cost is probably going to run about, and I'm saying this recognizing that I am the scientist. I'm not the I'm not the financial wizards of the company, but I have been told that it will run at about $1,000 to $1,200. It's less than the biopsy, a core biopsy. And the debate as to what it's going to cost is actually I was on a call today discussing it, and the price point is one of those things that I want it out and useful, so I'm happy to give it away cheap. My investors apparently want to make money.
Surprise.
Well, without the investors, we wouldn't be selling, so I can't argue too much. But no, I think it'll be my guess. My serious guess, it'll be between 1,000 and 1,200.
And where do you stand in terms of Medicare or other insurance?
We have, so this is a little bit of a complex and long answer. We have a very special arrangement in Puerto Rico, where the Puerto Rico government and ACES, which is actually the Puerto Rican equivalent of CMS, is giving us a code to actually sell the test there and provide it to most of the citizens in Puerto Rico at cost. So we will be doing that. That actually gets us into CMS because we're allowed to then get our own private code number. One of the problems that we've got with this test is if you actually look at the cost of the test and do what's called a crosswalk to currently available tests, the complexity of the test says it's similar to the Myriad test, okay, the Prolaris test. And the problem with that is that costs $3,800. And that's way more than any of us want to charge, because even our investors don't want to make that much money per test. So we're moving to do with the CMS. We're looking to get our own code, and it looks as though that's going to go along around about $1,000 to $1,200. Or we can use the generic code, which is actually just any molecular test, and do it about in $795. That's a discussion that's part political and part financial, and I stay out of that as much as I can.
Martin, could you comment on? I know you're talking specifically about your product here, but
yes.
Others, I'm sorry, your competitors, how are other liquid biopsy competitors of yours, and the availability that is on the market or not?
So the liquid biopsies, there are 4 or 5 of them that are available. Some of them actually don't use the exosomes. Most of them don't use exosomes. Exosome DX does use the exosome technology. They have a proprietary way of extracting the exosomes from urine. We use a fairly common commercially available extraction procedure. So they are charging, I think, $1,200 as well. And I may be wrong on that because I don't keep up to date with the prices that much. The other technologies that are doing these tests are looking at the cells that are released from the prostate into the urine, and they have the technology they use is actually an RNA-based technology, and they're charging about 900 to 1,000. Those tests do not actually distinguish between anything from what they do is tell you you have high-grade cancer or you don't have high-grade cancer. It doesn't tell you whether you have no cancer, and doesn't tell you whether you have intermediate or low-risk cancer. It just tells you you don't have high-grade. So it's not a particularly useful test for active surveillance. It's used extensively for people who have just had a biopsy and they've come back negative. And there's reasons, clinical reasons to suggest, in fact, that those patients have disease. It can be a very high PSA, for example, and they think, well, this needs to have another something else to test to actually confirm that it is negative. And so that's where those tests are mainly used. This is the only test that's been developed that actually classifies patients into low, intermediate, and high grade in a way that is not relying on biopsy and PSA. So the NCCN guidelines, which are the ones that all the urologists have in their, all the urology residents at least have in their coat pocket, it tells you that if you have a PSA of over 10 and you have the T-score that's over 2, tells you it's intermediate risk, and it's all based on, or high risk. Those are based on PSA and biopsy data. There's nothing that does it without the biopsy except our test.
And just to be, if you could clarify, you said you're going for approval, but you don't, but you think it'll be available before approval? I didn't.
Yes, no. So in the testing world, you can actually sell your test, provided you have been cleared by one of the agencies that oversees your lab test. There's one called CLIA, which is for any test that's sold in the States outside of New York. If you're in New York, or if the lab is actually built in New York and is run out of New York, you have to get New York state clearance, and that's called CLEP. And the two are different. CLEP is a more rigorous process. So we're moving into a lab right now in New Jersey. We're going to get we will get clearance before the end of the year. We will be able to sell the test by early January, I suspect. We will then get CLEP certification, and then we'll be able to sell to anybody in New York as well. So,
Say, Martin.
Yeah.
I've looked into this a little bit, and it seems like there's a vision of this sort of thing. Let's not be specific with your test, but this sort of thing.
I really don't want to proselytize my test. This is general, but I've given you the specifics here so that you can see what is possible.
Well, I want to talk about the vision. It doesn't matter whose test it is, but I mean, is it potentially replacing tissue biopsy and MRI and PSA?
So the idea with this is that it would be the first test run. Okay, instead of having a PSA, you'd have a PCC4 test, or whatever test happens to compete with us, okay, that does the same thing. That gives you much more accurate data than a PSA. It actually tells you from that very first urine that you have no cancer, or that you have low-grade cancer and should be on active surveillance, or intermediate grade cancer and you should consider active surveillance, or you have high-grade cancer and you should move to therapy. Now, no physician, no urologist I know of is going to be happy with just having a test that says, this guy's urine test tells me he's got high-grade cancer. those patients will still go for a biopsy to confirm this test. So it's not standalone completely, but it goes before and actually acts as a gatekeeper for patients who want to have a biopsy. And that you can avoid it if you have low-grade cancer. And you can be maintained either on watchful waiting if you're older or on active surveillance if you're younger.
And then just
For any test that's doing urine, by the way, this is anything but special to Mir. It's the urine is an obvious source for everybody.
now, one of our participants asked for clarification. Is this a genomic test?
So technically, so being very specific now, I refer to genomic tests as anything to do with DNA. So this does not measure mutations in the DNA. It doesn't measure familial relationships in terms of SNPs or otherwise. But what it is actually the product of the DNA is what's transcribed from the DNA is the RNA. So this RNA is what regulates the rest of the process. So there is another term that's used for it, which is another piece of jargon for everybody to learn. This is an RNomics test, RN-omics. It's RNA omics, not gene omics. So technically it's not genomics, but we actually start from the entire, all of the gene products that come from the DNA of what we're actually measuring.
So the net effect potentially is that men like us potentially won't need as many biopsies, right or wrong?
So technically, if you turn up with low-grade cancer and your test shows low-grade cancer, if you and your physician, and at this stage, I think it would take a bit of courage to do that without a biopsy. But if you and your physician look at this and say, I've got low-grade cancer, that from the molecular biology of the test, from PCC4 test, says that it's essentially like Gleason 3+3. You can argue whether that's cancer or not, because we've had that discussion at the beginning of the call. But basically what this is saying is you monitor the patient for a period of time, and all they have is Gleason 3+3. You can monitor them and never have a biopsy, okay? The only time you have a biopsy is when you reach an exit point. That's an agreement between you and your healthcare provider that you actually have got to a stage where you need therapy, okay? And that's when the PSA, not with PSA, when the PCC4 score crosses a second classification boundary, and absolutely when you've reached high-grade cancer. But a lot of patients in the US will actually cross over and have therapy when they reach intermediate status. But that's the decision that you and the physician take. And I would suspect that any time you cross that boundary and you're making that decision, your urologist will want to have a biopsy, a regular, almost certainly at that point, a fusion biopsy to see.
So Martin, you would envision, I guess, that a person would still, at age, 50, start getting their annual PSAs. This wouldn't replace a PSA, probably partially because of the cost. But then once a PSA indicates that there's a potential change, that then you would get the potential of a liquid biopsy and see what the results are there, maybe progress to an MRI, then progress, if you see something on our MRI or something else, then progress to a biopsy.
That's essentially the profile I would look at. I would just caution you though, if you remember at the very beginning, I said that there are 15 to 21, somewhere in that region, even up to 25% of patients who have PSAs less than 3 have in fact got tumors. And the beauty of this test is it doesn't rely on PSA. And we have done a study in Puerto Rico where they're taking patients with with PSAs of 1.5, and we can find, with this test, we can find the very small tumors that are high grade, identify them, and those patients can then go off and have a biopsy, and you're looking then for a tumor that you think is high grade, and that can often be seen on a fusion biopsy or an NPMRI. So one of the advantages of this test is it identifies patients that would otherwise be missed if you use PSA as a cutoff. So my ultimate goal is to replace PSA with this test as a general screen, and I know that's an extremely big lift, heavy lift, because PSA is dominant in the industry, and it's very difficult to say no to a quick, cheap test. But I actually think it puts people in the wrong categories, because they have the PSA, a high PSA can be from prostatitis, and you can land up going down the biopsy route. And once you're stuck on that biopsy route, it's difficult to get off of it. Okay, I think most of you will have, or some of you at least will have experienced that. Whereas if you take this test, it's not affected by prostatitis that we are aware of, and we've looked. So I think that's the advantage of just using this test. I think changing urologist practices is very difficult, and it'll be a long haul. But I think that's the future in the business.
Now, you mentioned in the course of things the GRAIL test.
Yes.
And they've been kind of high profile because I think they have a lot of powerful investors. But they just came out with a study, and if I remember right, they were able to use the test to identify, I think, 50 cancers. But when I read some of the news reports, I wrote a note to Dr. Klein at Cleveland Clinic, who was the principal investigator, and I asked him, what about prostate cancer? And he said that, that low-grade prostate cancers do not shed many cells. I was going to say tears, but that too.
That too, yes.
But, in your world, does the low shedding make a difference?
No, and the reason it doesn't is because we are collecting the exosomes, not the cells. And that makes a difference, okay? Because the exosomes are secreted from healthy cells all the time and from the tumor cells all the time. The only issue we have is that the number of exosomes that we could get in a urine specimen, if somebody voids first and then gives us a sample shortly afterwards, we need to have an hour between voids before we collect, because otherwise we don't get enough exosomes. It takes a while to build up again in the urine.
No,
the thing that's problematic, and this is what I worry about with the GRAIL test. I'm living happily now, and I don't want to suddenly find out I've got 50 different forms of cancer. You've got the problem with the GRAIL test and a number of other of these pan-cancer tests, from my perspective, is that most patients that have this, when they decide that they've got a tumor, they go back and then they have to go into what turns out to be a very poorly thought through sequence of events, because very often there is no way of categorizing the tumor. For example, and I mentioned pancreatic tumors, I'd love to come up with a test that would identify pancreatic tumors effectively and classify them, but just saying you have a pancreatic tumor does not help in treatment or management of the disease. And this is true for prostate as well, because they cannot tell you what kind of whether they know that it's probably high grade, but they can't do anything else in terms of where it is, location. You have to go back at that point and go back into the entire process. And because GRAIL is so new, and we're going to face the same issue too, because GRAIL is so new, everybody will fall back on the standard of care, and the standard of care has a built-in negative rate, miss rate, and so does GRAIL. And what you've got is two intersecting Venn diagrams where the actual impact is actually going to be minimal for a number of years. The technology that GRAIL has will eventually manage to do this if they stay with it. But it's an extremely complicated process, and it's going to be very expensive when they actually market it, I think.
Now, as it happens, I attended a webinar with Dr. Klein, and we asked him about your test. And he said, and you have to remind me here, he said, well, you know, they're recording results in the 90s. He says, I'm very skeptical of that. And
everybody is, but one of the differences between our test and all of the other tests, and this is the essence. Every other test, if you look at Polaris, they look at a total of 57 genes. If you look at Decipher, they look at 22 genes. We're looking at 442 genes, and we're not using standard statistical methods. We've developed a whole new way of doing the analysis, and that's how we classify. The classification, we're the only company that can classify, and the rates that we're getting, the way the methodology works, we actually set the sensitivity. In other words, if you have cancer, we detect it. We set that at 95%, and the test fails us. The actual whole process would fail if we didn't have that kinds of specificity. But we've set that, and then anytime you have a high specificity, normally you pay for that with a lower sensitive So if you have a high sensitivity, you detect the cancers correctly. It usually means you misdiagnose the patients as having no cancer, and you push them into having cancer, and that doesn't help it. That doesn't help that population. We've set the test up with a statistical methodology that allows us to segregate, identify the patients with cancer correctly, and identify the patients without cancer correctly. And that I know everybody says that the rates are very high. It's a very different methodology. I can go into the details, but you've probably seen ROC curves, the receiver operator curves. And those have actually derived, those curves go back to the Second World War. They're actually from the development of radar, where the signal you send out bounced off of an enemy aircraft and came back. So if you send out a very, very large, very energetic beam, it bounces back, but it actually changes and scatters, and so you get a lot of background. And that's where the receiver operator curve comes from. And basically, in all of the tests that people run, in all diagnostic areas, you actually try to find the sweet spot in the receiver operator curve, and that's where you set the algorithm. We don't do that. We set what we want it to be, and then we work on the mathematics to get it to that step. It's a very different approach.
So if somebody asks the question, you know, what amount of cancer do you have to have, or how sensitive is your testing? How do you address that?
So the answer is, if we can extract the microRNAs from the urine, which we can, the signature that we've got for the generalized signature for cancer is sufficiently different from the normal tissue that we find it with very high reliability. And it doesn't have to be a large amount of tumor. Keep in mind that when we're doing this, we're collecting all the tumor cells are secreting exosomes, all the normal cells are secreting exosomes. And what we're doing essentially is pulling out the exosomes and identifying the ones that have a specific complement of microRNAs and SNOs. So we're looking at a signature for that we've developed that's different from the normal tissue, and so we can identify that signature even if there's a very small proportion of exosomes present. And we're not working with highly expressed sequences which have vast differences from background. We can work in the region where they're in the background or close to background, because of the way the mathematics works in the signal recognition sequences we use.
I have a question here. You mentioned the 94% business. Is that from an actual clinical trial?
That's from a large clinical trial that we're in the process of getting ready to publish.
And that's out of Puerto Rico.
It's Puerto Rico the actual clinical trial that we're running this from is a trial that's on clinicaltrials.gov. It's running with sites in New York, sites in Georgia, and sites in Puerto Rico. So it's got a large Afro-American population and a substantial white population. And it's right now it's well over 1,000 patients in South.
Yeah, you just answered what I was going to ask. Accuracy wise, how does your result, compare to what the biopsy results actually show? The tissue biopsy.
The tissue biopsy, we have good concordance between GG1, GG2, GG3 to 5 with low, intermediate, and high rates. What we have developed with this test is an ability to look at the patients that have no evidence of prostate cancer from pathology. And we have been able to develop a signature for sort of a pan prostate cancer signature. And if you then look at all the patients have no pathological evidence of prostate cancer and screen them with that, we're pulling out all of the tumors that are essentially occult because the PSA levels or because the biopsy missed, okay? So we can identify those, which means that our concordance between no evidence of prostate cancer and no molecular evidence of prostate cancer and no pathological evidence of prostate cancer, that concordance is low, but it's low because we're identifying the tumors that are in those patients that have been missed by biopsy. So overall, it's got good concordance. We have very high sensitivity and specificity across all of the patients that have cancer. And where we actually don't agree is with the patients that have no 12 core negative biopsies, and we have positive PCC4 test, and we can classify those patients as low, intermediate, or high based on that. So that
I'm sorry.
Yeah, so that doesn't agree. That portion doesn't agree, but it's because of the misrate of biopsy, of needle biopsy.
Somebody else asks, with certain tests, they ask for the first urine of the day or something like that. Is, with these sort of tests, are they looking for urine or from certain time of the day, or does medication affect it, or does age affect it?
So a number of the other tests, and that's how I didn't talk about this, but some of the other tests require DRE massage. Okay, I avoid my physician because I don't like DREs. So, but, this is one of the issues. So the first pass is a fairly standard methodology, and it simply means that you have a relatively full bladder. And there is I think I don't think it's well documented, and I'm not even sure it's true, but the idea is that the exosomes tend to collect at the base of the bladder and are released first, which is why you get the first pass. An exosome DX sends you a rather elaborate collection system that allows you to collect the first pass, and then everything else is washed away. When I set this up, when Dr. Wang and I started doing this, I said, I want to have a test that is easy to take. And if we're going to do urine, I want to make sure that we can do it without massage, without first pass, just a regular routine urination into a cup. And we set that as a challenge. And I suspect that if we use DRE, we might get more exosomes from from the prostate massage. We've got enough that we don't need to go to that extent. And I think that that's one of the things that stops Exosome DX from and the other tests from actually being adopted, is because it hasn't really simplified life. For DRE, you really have to have a doctor's appointment, as opposed to this test, which you order it from the doctor orders it, we ship to the house, and you ship it back to us.
You either have to have a doctor or a real close friend, huh?
That's correct. That's correct.
So, I think we're reaching a time of wrapping up. Are there, Hugh or Jim, are there any other questions?
If I could ask one final one, I caught it right at the very beginning. You mentioned, Doctor, something about the correlation between vitamin D and maybe prostate cancer or something. And I was just curious if you could comment on that.
Yeah, so I get myself into a lot of trouble with my urology colleagues. Okay, I have studied vitamin D for a very long time. My other half is one of the world experts on vitamin D, and she runs the vitamin D conferences and has an active research lab. If you look at the prostate in detail, and this is getting a little bit odd now, but if you actually look at it, the first thing you should realize is that there are more vitamin D responsive genes in the prostate than there are androgen dependent genes in the prostate. So vitamin D, I refer to the vitamin D when I'm being annoying to my urology colleagues in conferences. I say the prostate is a vitamin D responsive organ that also responds to androgens. Okay, so that doesn't make me popular. One of the things we've shown in the lab, and these are lab studies, so you have to take them with a grain of salt in some respects. What we've shown is if you keep the level of vitamin D high and the levels of testosterone in the normal range, they don't have to need to be low normal, what you land up with is a prostate that has very little signs of cell division. Okay, there's no death, but there's very little signs of cell division. So you're causing the prostate to become homeostatic. It just stays the same size. If the level of vitamin D goes down, then what you discover is the level of the zinc transporter proteins in the prostate go down, and the prostate cells can then make a lot more ATP because the TCA cycle in the mitochondria is reactivated. And that ATP is the energy that the cell uses to undergo cell division, among other things. It maintains a lot of other things. And you cannot restore that once vitamin D is dropped off. The zinc transporters actually lose their ability to respond and maintain high levels of zinc in the prostate. So the obvious solution to a lot of this stuff is, in my view, and you have to talk to your physicians about this, but I believe that maintaining testosterone within a normal range in low-grade cancer is actually critical, but it only works well if you maintain your vitamin D status.
And will that affect your PSA score?
Not that I'm aware of. Now that if you maintain the androgen levels at a reasonable level, PSA is an androgen dependent gene. The kallikreins have androgen response elements in their promoter region. So if you maintain androgens, you will land up with a PSA that should be stable. If you add vitamin D, it should be, I'm using the term very loosely, stabler. But okay. We have not done a conclusive study on that. But the person that's done an awful lot of this work is Skip Trump, who was at Roswell Park for many years.
Was that Skip what?
Skip
You've
Trump.
heard the name before, Trump.
Trump?
Yeah. His actual real name is Donald Trump.
Yep.
I'll call him Skip.
But he's been Skip. He has been Skip for as long as, well, I've known him for 30, 40 years. He's always been Skip. but his real name is Donald Trump. Yes.
I'll tell you what,
So everybody usually asks me how much vitamin D do I take a day, and in the summer I take 2,000, in the winter I take 4,000 units a day, and I like it because they come in gummy bears. So I have 4 gummy bears in the winter and 2 gummy bears in the summer.
I'll tell you what, I think we're going to call it a night. We thank you for joining us, and we'll keep an eye out.
It was a great,
If anybody
great
has
discussion.
Yeah.
We've
If anybody
had,
has any other questions that they don't want to ask directly, you can look, if you look up Martin Tenniswood, Tenniswood's a rare enough name that you'll either if you just put in Tenniswood, you pick up my son or me. But Martin Tenniswood, and I'm at Martin Tenniswood at mearscientific.com. I'm more than welcome to answer your questions offline as well.
Well, thank you very much, Martin.
Thanks, Mark.
great discussion.
Well, thank you,
Appreciate
guys.
it.
I
Good
appreciate
information.
the opportunity.